Thank you very much. The topic of my presentation is multiscale study of morphology of a fracture surface aluminum magnesium alloy with consecutive dynamic and gigacycle loading. The influence of random statistic and dynamic loads on the lifetime of materials under very high cycle fatigue loading, 10 in power 9 up to 10 in power 10 cycles, so-called gigacycle fatigue, is a subject of much current interest for aircraft motor companies in the context of solving the problem of reliability of materials under real operating conditions. For instance, what concerns to the lifetime of estimation of gas turbine engine blades during their impact with solid particles, usually called foreign object damage. In this work, we investigated of influence of consecutive dynamic and gigacycle fatigue loads on the lifetime of aluminum magnesium alloy, dynamic preloading of samples was achieved in the split Gaussian pressure bar setup, and quasi-static preloading were carried out on servo-hydraulic tensor machine BIS. And fatigue tests were carried out on the resonance type of fatigue testing machine of Shimano at the frequency at 20 kHz. In this slide shows the samples and scheme of ultrasonic fatigue testing machine, and we can see mechanical properties of aluminum magnesium alloy MG6. This machine provides 10 in power 9 up to 10 in power 10 cycles, loading cycles with amplitude from 1 to several dozen of microns, and frequency at 20 kHz, which reduces the testing time in the comparison to the classical testing machine. In this slide, we can see dynamic preloading of the samples in the split Gaussian pressure bar setup, and we can see sample between the bars, samples after preloading, and some test results. This slide shows the dependence of the stress value on the lifetime proof value after quasi-static and dynamic preloading. Two samples were broken about 10 in power 9 cycles. This slide shows the characteristic surface relief of a fatigue fracture zone under high cycle fatigue and gigacycle fatigue, and we can see the fish ISO. And this slide represents the morphology of fracture surface obtained by scanning electron microscope. The sample number 2, when number cycles of about 10 in power 9 cycles, and we can see fisheye zone, and in this slide we can see a scale up fragment of fisheye zone. The chemical composition of aluminum magnesium alloy in the fisheye zone we investigated with scanning electron microscope Hitachi. From the radiation spectrum of reflected electrons using the Inca module, and as is evident of scanning electron microscope, the distribution of alloy elements is not uniform. In the region 2, in the center of the fisheye zone, the content of magnesium is 49%, and in aluminium is 42%. In the region 1, adjustment to a fissure zone, the content of aluminium and magnesium is 91% and 6% respectively, as it must be for Mg6 alloy. In the region 3, at the bottom of the fissure zone, the content of the aluminium and magnesium is 72% and 24% respectively. We investigated the other half of the sample, and in the center of the fissure zone, the content of magnesium is 41% and aluminium is 57%. And we support what a diffusion mechanism of cracking initiation, so-called Gorski effect, occurs under gigascale fatigue. In this case, having a larger radius magnesium atoms move to strature crystal and smaller radius of atoms aluminium in the compression of region. Or maybe its inclusion of intermetallic is present in the center of fissure zone. We used the new interferometer profile for qualitative fracture surface analysis, which provided the data allowing us to find correlation between mechanical properties and scale invariant characteristics of damage-induced roughness formed under high and gigacycle fatigue loading conditions. We used method was proposed by Zeiser and Bouchot. Its method based on analysis of the relief of fracture surface, which exhibits the property of self-affinity as manifested by invariant characteristic of surface relief. And in this slide, we can show 3D image of fatigue fracture zone inside the fissure zone. And we can see characteristic one-dimensional profiles, the dependence of KFR, where KFR is a correlation function, and represented it in logarithmic coordinates. We can calculate lower boundary L mean and upper boundary L max of correlation defects. And H is the Hurst exponent. Inside the fissure zone, the correlation length L max is about 50 micrometers. In the outside fissure zone, the correlation length L max is about 24 micrometers. And in this slide, we can see the population Hurst exponent and special scales LPZ and LSC at various levels of fatigue durability. We can see in center of the fissure zone the special scales is 0.5 up to 10.9 micrometers, and outside fissure zone special scales 0.9 up to 21.4 micrometers. And we can use these special scales for writing the kinetic equation for crack growth. The crack growth dl, our dl, is a function of phi of delta k stress intensity factor, E, Young modulus LSC, correlation scale in the ensemble of the defects, its correlation length L mean, and the LPZ, the scale related to the process zone. correlation length Lmax, it's LPZ. Dividing both sides of correlation kinetic equation for crack growth by LSC, we have similar very slow, where alpha is a universal exponent. And some conclusions. The comparative analysis of the scaling characteristics of samples loaded under conditions of high and gigacycle fatigue shows a significant decrease in the range of special scales, where the Hurst exponent remains constant for dynamically loaded samples in the Fisher's zone. This result confirms our assumption that mentioned characteristics LSFZ and LSC play an important role in the list of variables for the kinetic equation fatigue of the crack growth, and can be used for the identification of phenological parameters, providing self-similar law for the crack path. This supports the diffusion mechanism of crack initiation, so-called Gorski effect, occurs under gigacycle fatigue. Thank you for your attention.